Okay, we were talking in our last class about section 8.8, applications of Taylor polynomials. And we looked at this problem where we wanted to approximate the cube root of x function by a second degree Taylor polynomial about a equals 8. And we worked through the solution. And let me just kind of summarize what we came up with here. Let me summarize. Let me go to the whiteboard for our solution for this example. So what we learned, hold on here. Let me see, got to adjust that back. I can't get enough control on this thing. Sometimes you just have to use the mouse. It's just the way it is. Okay, so t sub 2, the second degree Taylor polynomial. Okay, so, well, let me just, hold on here. So our function was the cube root of x, and over the interval from 7 to 9, the cube root of x was approximately equal to the second degree Taylor polynomial. And we found that to be 2 plus a 12 times x minus 8 minus 1 over 288 times x minus 8 squared. Okay, and this the a that we used was 8. Further, the remainder, okay, the remainder, which is the absolute value of the Taylor polynomial minus the cube root of x, that remainder was guaranteed to be less than or equal to 0.00035, okay, over the interval from 7 to 9. So that means it's a pretty small error, okay. And of course, if we want the error to be smaller, we have to do a higher degree Taylor polynomial, okay. So what we can do is let's try out our T2, our Taylor polynomial approximation, to estimate the cube root of 8.24. Okay, now 8.24 is between 7 and 9. So the error, when we use the Taylor polynomial approximation to estimate the cube root of 8.24, the error should be pretty small. So how would we use the approximation? How would we use it? Well, let me show you here. Let me show you. I'm just looking here, making sure I have everything written down properly. I think we're good here, but let me just kind of double check. Yeah. Yeah, that's fine. That's fine. So, okay. I mean, let's say you have a computer and a computer's trying to estimate the cube root, well, the cube root of 8.24. Now, computers, as you know, work with flops. And arithmetic operations on computers are what? Adding, subtracting, multiplying, and dividing. The Taylor polynomials can be programmed into the computer to therefore compute, to estimate something like the cube root of 8.24. And so what I did was I said, okay, let's try out our approximation to estimate the cube root of 8.24. So how would we do that? How would we do that? Well, 8.24 is the x value that you're using. And so you just substitute that in wherever x goes in the Taylor polynomial. And then so again, we're going to get an approximation for the cube root of 8.24. Notice here on the right, when you compute all this, there's really no difficult math involved. And I actually, these values, these computations that I did, I worked them out all by hand. I worked them out all by hand and got 2.0198. This would be what a mathematician 200-300 years ago would need to do if they're going to compute the cube root of 8.24. This is how the mathematician would find it or estimate it. And of course, you can program a computer to do this too, right? I mean, how are these computers coming up with these answers? There has to be some algorithm programmed in the computer to do it. Now, if you put this on your TI-84 calculator or in Desmos, the cube root of 8.24, which I assume this would be a very accurate answer, is 2.019803.268. Well, you have accuracy to within 4 decimal places. So it just shows you the approximation is good. And that's how you see, that's how we can use these Taylor polynomials to help us. And by the way, I'll come back to this page. I'll just show this real quick so it's in the recording. Here on this page, all the math used in getting the 2.0198 answer is all just simple math. Okay, simple math that a human can do and also a computer can do, right? So are there any questions on this? The approximation, the cube root of 8.24 is approximately 2.0198. It's not perfect, right? But it's pretty darn good. Pretty darn good. So this is one of the things that we like to do with these Taylor polynomials. We like to use them to in applications to approximate needed values. That's one thing we like to do. Here. So let's look at another example here. Let me just see here. I'm bringing up, yeah, let's look at another example. Actually, the one I want to look at is, hold on, this one here. I want to do ones that I think you're going to have more difficulty with. This example is one. Let me let you copy this example down, and then we'll talk about it. Okay, so an interesting question. So again, you're used to putting in, like, you can put 69 degrees on in a Desmos or on in a calculator, compute the cosine, and you get an answer. How did you get that answer? What's involved in getting that answer? There has to be some algorithm, some programming behind that. It could be, for instance, a Taylor polynomial was used. So this problem's a little different, because if we compare this problem to the other problem we did in section 8.8, what are we not given regarding this fourth degree Taylor polynomial? What are we not given here? Let me take off my email. I don't want any distractions. Well, Jonathan, let me ask you this. Let me go to the formula here. Let me go to the formula. So again, this is this handout from, this is a handout. If you look in the course content in Blackboard, go to chapter 8, section 8.7. There's a link so you can download this handout. Here's the Taylor series formula. Incidentally, okay, Taylor series formula. What do we need to have in order to construct the Taylor series, to compute all those derivatives? I mean, our function is the cosine of x, right? Because we're trying to estimate the cosine of 69 degrees. So we know our function is the cosine of x, but what don't we have? If we want to find the Taylor series, the fourth degree Taylor series, well, of course, we're only going to use the first four terms of the sum formula. But there's something when we find those terms, those coefficients, for instance, there's something we need. That's right, Clea. We do not know what A is. We do not know what A is. What are we expanding our Taylor series about? What is the Taylor series of the function is centered at some value of A. What's the value? All right, we don't know. We don't know. So, okay, well, let's think about this a little bit. Let's think about this. Let's go to the whiteboard. Okay. I always have to get it in. So, all right, cosine of 69 degrees. First of all, let's get 69 degrees into radian mode. Because when we do computations, you work with radians. So to convert 69 degrees into radian mode, what's going to go on top here? We're going to multiply 69 degrees by something over 180 degrees. What's going to go on top there?
1.
That's, how about pi?
Oh yeah, I forgot.
Pi radians is 180 degrees. No problem. I appreciate all responses. And hold on. Right, Jonathan. Okay, very good. And so 69 degrees equals 69 pi over 180. See, the degrees simplify out, and you're left with radians. Now, 69 pi over 180, we could express that as 23 pi over 60. So what value of A is our fourth degree Taylor polynomial? Remember, it said it wanted a fourth degree Taylor polynomial. What value of A is the fourth degree Taylor polynomial centered at? Well, so we know that 23 over pi is going to be the x value, and we would like A to be fairly close to x, and we'd also like A to be a nice value. So let me just see here. Possible A values. Let me write it. Possible values of A. All right, well, let me see here. 30 degrees, 60 degrees, 90 degrees. So 30 degrees is pi over 6. 60 degrees is pi over 3. 90 degrees is pi over 2. All of those values of A can be used. You notice we're picking nice values of A that we can evaluate the cosine and its derivatives at nicely. But one of these values, and you notice I gave you 3. 1, 2, 3 values of A. One of them is going to be best. Which value of A is best? Best to use. Well, that's right, Yonatan. We would want the value of A closest to 69 degrees. And what value of A is that going to be? Pi over 3. Because pi over 3 is 60 degrees. Now, what'll happen in your homework is that a problem like this, they're not going to tell you what A is. They're not going to tell you what value of A to expand about, but there's a value that's better than the others. Okay? There's always a value of A that's better than the others, and that's the value that you'll need to use to get the right answer. So like, for example, let's say that you wanted to find the cosine of 42 degrees. Okay, what value of A would you use for the cosine of 42 degrees? What angle? So pi over 6 is 30 degrees, Susanna, that's right. And that's a nice value. That's one of those nice angles. Could there possibly be a nicer angle for 42 degrees?
40?
Well, what are, so like, let me list some nice values here. Nice values, 30 degrees. Ah, that's right, Gabriel. How about 45 degrees? Or pi over 4? Notice 45 degrees is closest to 42 degrees. You see that? So you have to try to pick an angle that's the best angle to center your polynomial at before you begin the work. Because if you pick an angle that's like not the best angle, then the WebAssign won't accept the answer because it's assuming you're going to pick the best angle, and the best angle would be the angle that's closest to your angle. Okay, are there any questions on that? Suzanne, are you good on that? Okay, excellent, excellent. All right, and all right, good Mark, good Gabriel. Okay, well then let's go to the solution here. Let's go back to the problem at hand. Keep clicking on the wrong thing. Hold on. I know how to do that. I'll just remove that file and let's. Okay, so again, we want the fourth degree Taylor polynomial to estimate cosine of 69 degrees. And then, of course, we're going to ask how accurate is this estimate? I mean, that's an important question too, right? And we know Taylor's inequality is going to be involved in that. So, okay. So since 60 degrees, is the closest ninth value to 69 degrees, we will expand our Taylor polynomial about a equals pi over 3. So to get a fourth degree Taylor polynomial, I have to take the function cosine of x and find its first four derivatives. And then I'm going to evaluate the function and its first four derivatives at a equals pi over 3. And that's going to allow me to get those values. So let me give you a moment to, catch up here. Please let me know if you have any questions, okay? So of course, what I did here is I put in a 30, 60, 90 degree triangle with legs 1 and root 3 and hypotenuse 2. And that just helps me then get the values. So WebAssign, of course, is going to want simplified radical form for the sines and cosines of those angles of pi over 3. Well, now that we have what we need, we can get our fourth degree Taylor polynomial about x equals pi over 3, right? Sorry, one moment. Okay, I was trying to put my phone on silence, but I guess I just turned the volume way down. All right. So yeah. So let me just maybe add a few details here. Okay, so this is f of pi over 3 here. F prime of pi over 3. Negative 1/2 is f double prime pi over 3. Root 3 over 2 is the third derivative evaluated at pi over 3. And then the 1/2 is the fourth derivative evaluated at pi over 3. So we're just using the Taylor polynomial formula. That's all we're doing. And of course, a here, a was equal to pi over 3. So this is a polynomial, and it's a fourth degree polynomial because the highest term is x minus pi over 3 to the fourth power. If you were to like multiply that all out, you would get an x to the fourth, you would get an x to the fourth power here, right? And so fourth degree Taylor polynomial. Now, naturally, what we want to do is we want to simplify those coefficients. We do want to do that. So let's see. Let me just see here. Are there any questions? All right. Let me just. So 2 factorial is 2. Okay. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. So the coefficients are going to simplify to, well, negative 1/2 divided by 2 is negative 1/4. Oh yeah, and here this will just be 1 factorial is just 1, right? So this will just be negative root 3 over 2. Because 1 factorial is 1. Let's see, let me continue here. Root 3 over 2 divided by 6 would just be, what, root 3 divided by 12. And then 1/2 divided by 24th, that would just equal 1 over 48. Okay, are there any questions on that before I have that written on the next page. I mean, those simplified coefficients. But are there any questions before I go to the next page? Okay, to the next page then. So now the cosine of x is approximately, notice we have approximately here, that is equal to the Taylor, approximately equal to the fourth degree Taylor polynomial. Okay, and I should say, I should really qualify that. It isn't, the polynomial is not going to be a good approximation everywhere, but certainly about some interval around pi over 3. Okay, and we know the cosine of 69 degrees is 23 pi over 60. So I want to find the cosine of 23 pi over 60. That's my x value. So that's what I'm going to feed in, put into the Taylor polynomial. Everywhere there's an x, I put in 23 pi over 60 in the polynomial. Now it turns out that 23 pi over 60, for every parentheses, you'll notice that you have 23 pi minus pi over 3. Well, pi over 3 is the same as 20 pi over 60. If you multiply the top and bottom by 20, pi over 3 is the same as 20 pi over 60. And that allows you to subtract the two fractions here to get 3 pi over 60 or pi over 20. So we could say then that the Taylor polynomial evaluated at 23 pi over 4 is equal to what you see here. Okay. And we have to work that out. So I'm going to go to Desmos. Okay, I'm going to give you a moment to copy. Let me go to Desmos and get a head start on evaluating that. WebAssign is going to look for you to evaluate exactly this. Okay, exactly that. Okay, so one moment. When you get this copied, go to Desmos and type it all in and see if you get this answer 0.3583686. That's what I'm doing now. And I'm going to bring up my Desmos, but take a few moments at home there and let's see if you can get that answer too. Let me bring up my Desmos here. Well, you got to be careful. You hit that X, and it's like it kind of gets rid of it, right? So let me see here. Let me go in Desmos. Okay, so I'm going to, try to get that answer. So the polynomial was what? 1/2 minus square root of 3 divided by 2 times pi divided by 20 minus 1/4 times pi divided by 20 squared. Getting there. Plus square root of 3 divided by 12. Hopefully this is all getting recorded here. Yep, it is. You're following along with me, right? I divided by 20. One moment here. Cubed. Let me see. All right, I assume that was a yes. I heard a beep. I assume that was a yes. Okay, and then we got one more term. See, WebAssign's very picky. It's gonna, you're not gonna be able to trick it or anything. You got to type all this in. As you should. Yeah, 0.3583686. And then there's more, but if we round it to 7 decimal places, that's the answer. Okay. Was there a question? Was there a question? Who did get that as well? Who got that as well? In Desmos. All right, Clea, very good.
Professor, we can also check it by taking the cosine of 23 pi over 6, right? Because I did that and I got the same number.
Well, no. So there will be agreement, right? There will be agreement, but but you need to go through this process. Well, you should go through this process, and also for the work, like for the final exam, I'll be looking for that there. I mean, I know what you're saying. You're saying that that there's going to be agreement to a certain number of decimal places if you just computed it like with the calculator, right? But you're not supposed to do that, Clea. Okay, if that makes sense, you're supposed to do it this way, but I mean, it would make sense. There would be. It's an excellent question. Certainly on the final exam, the work, I would want to see that work there on your paper, and then you'll get your answer. But I wanted to show how many found this helpful that I showed this on Desmos at least once, so you can see how to work it out. How many feel that was helpful? Was that helpful? Okay, Avery. Thank you, Avery. Good, good. Thank you, Victoria. All right, all right. So the question is now, how accurate is this? How accurate is this answer for the cosine of 69 degrees? Well, we're going to need to use Taylor's inequality. Okay, so let me go ahead back into the files here. go back here. So on the handout, Taylor's inequality is at the bottom. Now it's actually in the textbook, oddly enough, it's located, it's introduced in section 8.7, not 8.8. But the error in the approximation will be less than or equal to the error bound on the right side. The error bound on the right side is m divided by n plus 1 factorial times the absolute value of x minus a to the n plus 1 power. How do we, the m is the part that's the most hard for students to find, but all you need to do is say, okay, m has to be greater than or equal to the absolute value of the n plus first derivative of x. Well, in our case, since we're working with a fourth degree Taylor polynomial, we would need then for our function, which is the cosine of x, we would need to find the fifth derivative of x, which is not hard to do. So let's go here. Man, hold on. I don't want unnecessary stuff here. Remember, when you found the Taylor polynomial, you were already worked out to the fourth derivative. The fourth derivative of the cosine function is the cosine. It repeats, right? So the fifth derivative of the cosine would be negative sine. And so we ask the question, how accurate is this Taylor polynomial approximation? How accurate is it? Well, we're going to use Taylor's inequality. A was equal to pi over 3. And the fifth derivative of x is negative sine. The absolute value of negative sine, m has to be greater than or equal to the absolute value of negative sine, okay, which would just be, I want to be a little bit careful here. Well, it would be that, okay? And the sine or cosine waves never, the amplitude is 1, right? So sines and cosines never, like just the regular sine or cosine function, never goes above 1 or below negative 1. So the absolute value of negative, and that's true for then the negative sign, right? The negative sign function never goes below 1 or above 1. So the negative sign can't get bigger than 1. Okay. So the absolute value of negative sign can't get bigger than 1. So you take m equal to 1. So this is one of these problems where you're not going to look at where the fifth derivative is increasing or decreasing. You're just going to say, hey, I have the absolute value of negative sine. Sines and cosines never get larger than 1. So m equals 1. It's that simple. That's the m that you're going to use. And so here is the m. Okay. And the x is, in this case, 23 pi over 60. You're at a specific value of x that you're looking at, 23 pi over 60. So that's what x is. A is pi over 3. And the 5 factorial, of course, is 120. Because 5 factorial is 5 times 4 times 3 times 2 times 1. That's 120. And so the error in your approximation is less than or equal to 100, I'm sorry, less than or equal to this. 1 over 120 times pi over 20 to the 5th power. That will equal 0.000000797, and that is less than 5 over 10 to the 6th power. So our estimate is correct to 5 decimal places, which is why, Clay, you might have noticed on your, like on the calculator, it gave you something very close to our approximation, right? Because our approximations vary, it's correct to 5 decimal places. So, you know, trigonometry is used a lot in astronomy, right? You have angles to stars, you adjust the sextant or, you know, the telescope. That's actually surveying is the sextant, right? But surveying, astronomy, you're always looking at angles, and, you know, sines and cosines are important. So a 4th degree Taylor polynomial would allow a mathematician to estimate the cosine of 69 degrees correct to 5 decimal places. What if we wanted to have something correct to more decimal places? What if we wanted our estimate correct to, say, 10 decimal places? Well, what would we have to do? If you want a better approximation, what can you do to the Taylor polynomial? What can you do? You can't adjust A equals pi over 3 is the best you're going to do in terms of a nice angle that you can easily evaluate the derivatives at. But what can you do to improve the approximation? That's right, OPME. Very good. Increase the number of terms. Use a 5th degree Taylor polynomial or a 6th degree Taylor polynomial. And the thing is, every polynomial you use, you can use the Taylor's inequality to get an idea of how accurate your estimate would be. Okay, like sort of what would the worst case be? Okay, you get an idea of how, of a guarantee on how accurate your estimate is. Now, let me ask you this. Well, are there any questions? Any questions at all? All right. Do we have, let me just go back to this let me go back to this Taylor polynomial. Do we have an alternating series? I mean, sorry. Are the terms of this, well, what I'm trying to say is, does this polynomial appear to be a polynomial where the terms are alternating between positive and negative? The answer is no. That's right, Jan. So you can't use like the alternating series estimation theorem to help you here. You have to use Taylor's inequality. Taylor's inequality is more general than the alternating series estimation theorem. Okay. They incidentally in the book, I mean, this is something that we won't cover here, but in example 3, they talk about using the Taylor. Let me see here. Well, no, that one involves a binomial series. You don't worry about example 3. I mean, basically, I think we've covered 8.8 pretty well here. Overall. Are there any questions before I stop the recording? Okay, let me stop the recording then. Excellent.